I'd like to review just enough content to really get a hold of numerical problems that involve metric conversions in scientific notation. So the idea or the purpose behind this video is to cover scientific notation just enough so that you can actually get to converting standard notation into scientific notation and scientific notation into standard notation, as well as moving onwards to using that knowledge and to sort of incorporate that in prefix to base conversions or base to prefix conversions, or even prefix to prefix conversions. And if that sounds like gibberish, then I'll actually be going into what those mean just enough so that we can get some problems done. So it's not going to be rigorously in depth, but it's just going to be just enough to get the procedural aspects of the question down and done. So first and foremost, scientific notation. The purpose of scientific notation at its heart is to reduce the amount of writing that we have to do when writing big numbers. So if you have, suppose, 0, 0, 0, 0, 3, 2, 1, or let's take something more realistic, 3, 7, 4. This is an insanely small number. And what scientific notation helps us do is it helps us write this number in such a way that we don't have to write all those zeros, because we could get really small. We could have a lot of zeros, and that gets tedious. So the basics behind scientific notation is following a procedure to get something written so that it is multiplied to 10 raised to a power of something. So essentially what we do is we take the decimal point and we move it such that there is one non-zero number to the left of the decimal point. So where would we need to move the decimal in order to get there? Well, we would need to move it right here. So we would move it once, twice, 3 times, 4 times, and 5 times. So on the 5th time, we have moved the decimal such that there's one number to the left of the decimal, and it's a non-zero number. So really now we have 0, 0, 0, 0, 3.74. And you'll notice that we moved it 5 times. So we essentially take this number and we sort of ignore the zeros. We take this number, 3.74, and we multiply it by 10 to the power of something. And that's really where this stuff gets important. It can either be a power to the negative number or a power to a positive number. And the number itself is going to be how many times you had to move the decimal in order to get to a position where to the left you have one non-zero number. So that number in particular is 5, because we had to move the decimal 5 times to get to that position. 1, 2, 3, 4, 5. Now, what do we choose? Do we choose negative or positive? Well, we actually choose negative because we want our scientific notation to represent a very small number, because this is a very small number. So we choose -5. So it's 10, so it's 3.74 times 10 raised to -5. And we can actually check this in a site called Mathway. So if we take our number here, 3.74 times or 0.00003.74, we had 0.0000374, and this will convert it to scientific notation. You can see that's 3.74 times 10 to the power -5, which was our answer. Now, suppose that instead of having a very small number, we had instead a big number. For instance, I'm just going to write a random number here with several zeros. Now, that's very tedious to write. Scientific notation would tell us that there is in fact a decimal here, and that's implicit in all numbers. There is in fact a decimal after the number, even though it's not explicitly written there at times. And we want to move the decimal such that there is one non-zero number to the left. So we're following the same rule. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. So now our number is 4.63 times 10 to the power 9. It's to the power 9. Now, should we put a negative? Well, no, we want it to represent a very big number, so it would make sense to have a positive there. So that's how we can go from standard notation, that is, of course, the notation that we are all used to, these numbers here. That's how we go from standard notation to scientific notation. That is to say, the notation where it takes a particular number and multiplies it by 10 to a power of something. And if you were to do this multiplication, then you would get this number out. Now, that's standard notation to scientific notation. What if instead I said scientific notation to standard notation? Well, I would essentially have, for instance, let's say 6.4 times 10 to the power negative 9. Or let's, for purposes of simplicity, start with positive, let's say 4. Now, essentially what we want to do is we want to take this number off to the side, 6.4, and we essentially want to, again, we want to move the decimal. Now, we can either move it this way or we can move it this way. Now, what we want to do is we want to move it 4 times to the left or to the right. Now, since we want to represent a big number, we're obviously going to move it to the right, right? Because the place value decimal system goes from ones, tens, hundreds. As we move to the right, the number gets bigger. So we're going to represent this as a big number. So 1, 2, 3, 4. We moved it 4 times and we filled the pockets in with zeros. So our final answer is 64000 or 64,000. And again, take nothing at face value. We can go ahead and prove this here. We'll take 6.4 times 10 raised to, I believe what we had was to the 4th power. Convert to regular notation, and we get our answer back. And so that allows us to go from standard notation to scientific notation. And I'm going to do this same example, but with a negative exponent so that we can have best of both worlds. So let's go with -6 this time, and we want to have standard notation from this point. So we'll take 6.4, and again, we want to either move 6 times to the left or to the right. But since we're representing a small number, it would make sense to have zeros to the left instead of to the right, because to the right would essentially increase the value of our number. So we go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So 0.1, 2, 3, 4, 5, and then 6, 4. That is essentially our number. And of course, we could check this. So we'll go back to our trusty math way, and we will say 6.4 times 10 raised to the -6th power. And you'll see that's exactly what we get back. So that's standard and scientific notation, and of course, converting. Now, I'd like to touch on something, and that is to say that this is scientific notation. This is scientific notation. This, a random number, is not scientific notation. Now, is it because I have 3 digits? No, that's not true. The fact of the matter is that scientific notation tells me that the decimal should be moved in a position where there's only one non-zero number to the left of the decimal. Here, there are 2 non-zero numbers to the left of the decimal, so this is not valid scientific notation. In order to fix this occurrence here, what I need to do is I need to move the decimal 1 place to the left to ensure that there is 1 digit that is non-zero to the left of the decimal, 6.41 times 10 to the power -9. Now I have fixed my problem, but I need to add 1 every time I do that. So my real answer is 6.41 times 10 to the -8, because -9 plus 1 is -8. Let's take a more rigorous example in order to demonstrate this procedure. So what we're going to do here is we're going to take 2.108, or let's just take 8 here, times 10 to the power negative, or let's say 6. So we want to ensure that the decimal is placed in such a position where there's one non-zero digit to the left. So 1, 2, right? Now we're going to have to add 2 here. So 6.4218 times 10 to the power 8. And that is our improved scientific notation. So now that we know everything about scientific notation, let's get into this mess. So the basic rundown is that we have something called bases, or let me start with prefixes. Prefixes. Now, this should be intuitive that the word pre means before something. And those prefixes you've probably heard before, like, for instance, nano, or micro, or milli, or even centi and deci, or even kilo. And so we have these prefixes, but they don't actually mean anything in and of themselves. They don't actually have a value. They only really have they have values, but they're prefixes. They're add-ons, and they're add-ons to something called bases. And these bases you've probably heard before as well, such as a meter, right? Let's see. So a meter, or and there are of course many bases. Let me pull up some just to get all of them down. Meter, let's say liter, and gram, and of course there are more, but these are just sort of an example of the base units in distinction to the prefixes. Now, we can take these prefixes and attach them to the meter, and our idea of how much a meter is, or how much of a particular amount we have, will change. So essentially, so these prefixes have predetermined values, and these values here. So for nano, it's 10 to the -9, and for micro, it's 10 to the -6, and for milli, it's 10 to the -3. And then it's 10 to the -2 for centi. And for deci, it's 10 to the -1. And for kilo, it's 10 to the negative, or 10 to the +3. And so the idea is that you can attach any one of these to any one of these bases. So for instance, we could have a nanometer, right? A nanometer. Or we could have a milliliter, or a centigram, or a kilogram, so on and so forth. And essentially what you would be doing to the amount of a meter, if you were to attach a nano, if you were to have a nanometer, you would be adding on to the value, or in this case, you're making a meter. If you think of a meter, you can subdivide that into these many times, and then one segment of that would be a nanometer. And so that's essentially what you're doing. But our concern is to essentially convert between them. So we want to be able to say that, we want to be able to say, okay, let's see, 6.34, let's see, meters is how many nanometers. So this relationship here, this relationship is of a base, right? We took a base and we want to convert it to a prefix, right? That's our relationship here. So we're going to go ahead and do that. And the basic idea procedurally, and of course we can go more into why this works or what it means, but procedurally at least, we want to essentially, what we're going to do here is we are going to take 6.34 meters, and we want to set up a conversion factor. And the conversion factor is going to be 1 nanometer. It will essentially be equal to 1 times 10, and then we pick off what a nanometer equals, which is 10 to the -9, 10 to the negative 9 meters. So essentially, we're having a conversion factor here, which is to say that 1 nanometer is equal to 1 times 10 to the negative 9 meters. Okay, so if I had nanograms here, well, 1 times 10 to the negative 9, this would be grams. So 1 nanogram is equal to 1 times 10 to the negative 9 grams. Similarly, if I had, let's say, if I had 1 let's see, 1 deciliter, that would essentially be 1 times 10 to the negative 9 liters. So you're essentially converting this into the base equivalent, okay? And then you're using that as a conversion factor. And so here we can say so we can set up a conversion, which is 1 nanometer is equal to 1 times, and you lift that number off the table, 1 times 10 to the negative 9 nanometers, or sorry, meters, which is the base value. So we're using that conversion here, and we do that in such a way so that our meters cancel out and we're left with nanometers. So our meters essentially cancel out, and we have, it's now, we have 6.34 times 1 over 10 to the power negative 9, which we can say is 10 to the 9th, right? And so that's our scientific notation, and you can see that the 6 or the decimal has 1 non-zero number to the left, and that's essentially what we wanted. And so we can leave it like this, or we could switch it back to standard form, and we'll do both. But let's go ahead and verify this. Let's really see if 6.34 meters is these many nanometers. And of course, we can always verify that online. So we are going to go to the internet here, and so I believe we had 6.34 meters, and we wanted nanometer. So it says 6.34, and then it says this E means 10 to the power positive 9. And that's actually what we had, right? So so this is a base to prefix conversion, right? We make a conversion that way, and that should get you through all base to prefix conversions. But what if we had prefix to prefix, right? Prefix to prefix, and we have an example here, 224.5 nanograms. So 224.5 nanograms. Oh, I believe that's right, nanograms equals how many micrograms? So the basic idea in this case is to essentially take our 22.4.5, convert it to grams. Now it is in grams. Let's see. Now it is in grams. So when we do this, when we convert it here, when we pick off, well, this wouldn't be to the negative 3, it would be to the negative 9. Now it is in grams. So when we pick off that nano off the table here, we're actually just converting it to the base unit. So if this were nano liters, I would say that 224.5 times 10 to the negative 9 liters, right? I would say the base. And I'm essentially going to multiply that. I'm going to multiply that by 1 microgram. Okay, 1 microgram is 1 times 10 to the negative. Well, now I'm going to lift the micro off the table, and the micro we know is 10 to the negative 6, 10 to the negative 6. So essentially, all I'm trying to say here is that, you know, you want to make a ratio, right? you want to make a ratio. And so what you're saying is, okay, well, you know how much 1 microgram is in terms of grams, right? Because I said that if you have a microgram, right? If you have a microgram, then 1 microgram is essentially equal to 1 times 10 to the negative, and then the amount that micro would be, which would be -6. 1 microgram is equal to 1 times 10 to the -6 grams. It's the base unit. So you take the, you essentially take the prefix, you're sort of ignoring the prefix, and you're saying that, well, 1 times 10 to the -6 is the gram, it's the base unit. And you're using that here so that you can convert. The only difference is you have to go through grams as well. So you're converting the grams over here so that you can cancel out grams. And so essentially what you're doing at this point is the grams cancel out. And now what you have is 224.5 times 10 to the -9 over 1 times 10 to the -6. And of course, this unit is entirely in micrograms since our grams essentially canceled out. And now all you have to do is take care of the exponent. So you could have 224.5 in your answer, as you naturally would think, except you just subtract the exponent. So when you divide, if you remember your exponent laws, a over b, let's see, and you have z here and n here, this will equal a over b, z minus n. Okay, so you always have to take the top and subtract it, take the bottom and subtract it from the top. So it's going to be 10 minus 9 minus 6, or minus 6, right? And that's going to be everything we have here times 10 to the power -3. So we have 224.5 times 10 to the power -3. That's our answer. But again, it's not in scientific notation because the decimal point has to be in such a position where there's only one non-negative number to the left. So we need to move it 1, 2 spots, and we'll add 2 here. So we have 2.245 times 10 to the -1st. Okay, because we had to do this here. And you'll see that 2.245 times 10 to the -1st is our answer. And of course, this is the valid scientific notation form. But what we could do is we could essentially express this as a standard number. So we have 2.245 times 10 to the -1. So where would I move this decimal? Should I move it this way or should I move it this way? Well, naturally, I'd want to move it this way because the negative signifies the number is small. So 0.2245 is our answer. So 0.2245 micrograms in 224.5 nanograms. And hopefully that's useful, and hopefully that matches what we have. And so now what we've done here is we've went base to prefix, and we went from prefix to prefix. Now let's go to prefix to base. Okay, so here we have an example, 14.3. 14.3 centimeters is how many? And I believe we have meters. So we essentially want to establish a proportion here. We want to be able to say 1 centimeter is equal to X meters. And so what we'll say here is that we'll say, okay, well, 1 centimeter is equal to 1 times, and we'll lift it off the table, that's centi, 1 times 10 to the -2 meters, right? We're getting that base in there. And this is our conversion factor. And now it just really becomes a piece of cake. We'll say 14.3 centimeters, we start with, we get what we start with. And that is going to be 1 centimeter is equal to 1 times 10 to the negative 2 meters. So we're using this conversion factor because if I had put this here, then that wouldn't work. And then our centimeters cancel out. We're left with 14.3 times 10 to the negative 2. But we have to, we essentially have to ensure that this is in scientific notation. So we're going to move that to the one spot to the left, and we'll add 1. So we'll say 1.43 times 10 to the negative 1. Or, so this is valid scientific notation, or we could say 1.43, right? We'll move it one spot to the left because this is negative, 0.143, right? 0.143. So these are both valid answers. It depends on where, essentially, these are both valid answers. It depends on what your question is asking. And so it seems as though in our answer here, we had 14.3 times 10 to the negative 2. And we moved it 1 to the right. We should have added 1, right? And that would have made it a negative 1. And then everything should have played out as it played out here. But that is the basic answer. So let's go ahead and check that on the internet. 14.3 centimeters. So and it seems like we are right on the money here, 0.143, 0.143. So that's the main 3 processes that we want to follow, or the 3 main categories of how these conversions are essentially, how they manifest themselves. Base to prefix, prefix to prefix, prefix to base. That's really all you're going to see here.